Recording. I have to start recording because this is Haskell. This is Haskell. And who is this? This is Connell Elliott. Sorry for the long break. Sometimes I stutter, and that's why the long break. But still, his name is incredible. A Galilean revolution for computing. He's really cool. Like he's the stuff what he says. I had to post. I type. Oh, what's happening? No, I had to type. I was typing today what he said. Because it's just it really puts things. Oh wait, I have one notification. Who has tried to favorite your post? Yeah, right. Like this stuff. Yeah, I think there is a strong overlap between functional programming and formal methods. No, you know what? I should just leave him to say this.
The discussion is going to be a bit.
Right.
We used to refer.
He's amazing.
And there is some
check this out.
server or operating systems people sort of say that, okay, I'm interested in formal logic or category theory or something like that. So what do you think is behind something like this?
Yeah, I think there's a strong overlap between functional programming and formal methods, and I think it's because there's a sort of shared heart of intent between the two, which to me is really understanding computation in powerful and practical ways. So I think we've known since the 50s, 60s at least, that the imperative model of computation makes rigor, makes certainty about computation impractical. So it's sort of doable in very small toy languages, imperative languages. But if the language gets more realistic or the problems get more interesting, the imperative paradigm itself thwarts the ability to work with certainty, to work correctly with computing. And so that was a huge part of the motivation for our field of functional programming. And then, Haskell in particular was taking a really sort of purist approach. And we used to refer to Haskell as our motto was good for equation reasoning. So we were really talking about the fact that programming can be mathematics. So you can have math, logic, the tradition of Euclid and much later, and especially to the 20th century, when we really understand what proof is about. So we have that tradition. And then in the middle of the 20th century, we got automated computation. So that was a huge deal. But the very early models in which computation was founded, they reflected the original machines. The original machines were very weak and unreliable. And so the languages directly reflected them simply because we couldn't afford abstraction. And that was what we call the von Neumann model of computation. Now, I mean, no disrespect to John von Neumann. He was brilliant. He invented massively parallel computing as well as the sequential model. But by starting with the sequential model, we made, I think, certainty an impractical enterprise. Functional programming was about rescuing that intent and putting it into practice. I think we've drifted away from that kind of basic aim, basic values, but that's what got us started.
It's so amazing. Okay. I don't know. I just love, his talks are great inspiration. And I sometimes, I know we are supposed to build things, because I'm told you're supposed to build something, and that's a great way to learn. But after I watch a talk by Connell, I go immediately and read something from him, or like start and learn, categories and just like really get to the bottom you know of it, and it's really inspirational. I guess each every time when we learn, guess it's good to, no, I don't guess, I mean it's good to start with something inspirational, right? Like with a good motivation. So learn you a Haskell, right? Learn you a Haskell. And last time, it was such a long recording. Where's the updated one? So yeah, when you go learn you a Haskell for great good, there is up to date. So there was such a, actually there was such a, holy shit. It was such a long recording. Only about the conditional expression and how the he 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 worded it. An intro to lists, baby's first functions. The whole thing was about this, right? So now we're going to make a function that multiplies a number by 2, but only if that number is smaller than or equal to 100. And the condition kind of looks different than what's said here. I mean, it gives the same result, right? But it's like this smaller than or equal to 100. It's like the dual of this. Otherwise, it's larger than 100. So I actually found this very confusing. Confusing in the sense that it's not that it's not clear, it's clear. But confusing, maybe that's a bad choice of a word again. It's that I have to stop. I have to stop and think. Oh, okay, I get it. But why do I have to stop and think? So I would rather that the words themselves reflected the condition in the code. Okay. So okay, let's just continue, right? Yeah, we did this too. It's just the same conditional but plus 1. And it was about the parentheses, right? Because if there were no parentheses here, then this plus 1 would be actually contained within the else branch. But when we put the entire code into the parentheses, then we add the whole result of the function and we add plus 1 to it. Okay. Had we omitted the parentheses, it would have added. Well, yes, we did this too. We did the. Okay, an intro to lists. Yeah, we stopped on lists. You see, it's been a couple of days. I had some trip. I had a trip and stuff to do, life stuff. And so now I'm back at lists, right? Milk, bread. This is spelled wrong. Have you noticed this? Bread, eggs with 1 G, and a dog. Okay, much like shopping lists in the real world, lists in Haskell are very useful. Am I recording? I am. Lists in Haskell are very useful. It's the most used data structure, and it can be used in a multitude of different ways to model and solve a whole bunch of problems. Lists are so awesome. Oh, okay. In this section, we'll look at the basics of lists, strings, which are lists. Yes, strings are lists. Why are strings lists? Because strings are a list of characters, right? Let's go to CD. Oops. Haskell? No, it's in dev. Haskell, CD, Haskell, CDL. Yeah, okay. So if we have like a string, let's say apple, the word itself is a list of characters, which are A, P, P, L, and E. In that sense, it's a string. And I think it's like, can we add the things like a list? Wait, A plus, maybe like this. This is cool. A plus, can we do this? Can we do this? A, B, no, wait a second, B, E. Let's just do with the AP. Parse error on input. Oh yeah, I can do it like this. Can I do like A? Wait, I have an A, right? If I add an A to AB, what do I get? No instance for semigroup arising from the use of in the expression. Can I do it with a plus sign? Couldn't match expected type with actual type char in the second argument of plus. Maybe I can do it. Can I have a list of a string? Oh, a list of a character is a string, but there is only one character. This is interesting. Now, is this the same as this? Couldn't match exact type character in list with character. Expected character, actual string. Yeah, not sure about this. Let's just continue. Yeah. So, but yeah, it's in the sense a string, it's a list of characters. Yeah. In this section, we look at the basics of lists, strings, which are lists, and list comprehensions. In Haskell, lists are a homogeneous, I'm not sure how you read this, homogeneous data structure. It basically means that it's of the same type, I think. Let's also open Chat GPT, because I have the new one, the O, and I think it's pretty good, and it's a good idea to, okay, try it now. Yeah, okay. So homogeneous. It's a type of a data structure that contains elements of the same data type. Yeah, it has the same data type. This consistency ensures that operations performed on the data structure can assume a uniform data type, leading to efficient processing and ease of implementation. Homogeneous data structures are prevalent in many programming languages and are foundational to computer science and software development. So the thing about this is we had like the conditional expression itself. So if 2 plus 2 is 4 is 5. If 2 plus 2 is 4. No, wait a second. Let's just make this simple. If true, then true, else false. So true. So if true is true, then true. Else, if true is not true, then false. But if you see, the whole entire conditional expression has the same type. It's a Boolean, so it's true, true, and false. Yes, if something is true, then that something is true. So we're not actually going inside of that. Why is that something true, or what makes it true? Otherwise, that something is not true, it's false. So it's the same type. So one of the things is you cannot write if true, then true, else 1. You see, you cannot do that. Or if true, then true, else apple. It won't work because this is a string. Look at this, couldn't match the type character with bool. Actual string, and this is a bool. So it expected a bool. Okay. So it's the same with lists. So lists are a homogeneous data structure. They store several elements of the same type. That means that we can have a list of integers or a list of characters, but we can have a list that has a few integers and then a few characters. Excuse me, that means that we can have a list of integers or a list of characters. Okay, we can have a list of this So it's like we can have a list of pairs, or we can have a list of yeah, same type. But we can have a list that has a few integers and then a few characters. I think this few is maybe confusing, or it is like in the sense of a few of these. It means that it cannot be mixed. Like you cannot have, you can have a list of A, B, C, right? This is A, B, C. So yeah, it will be like A, P, P. Oh, P, E, apple, right? But you cannot have like A and then 1. It won't work. It would work if this was a tuple, right? Then it will work, because tuple can have an arbitrary number, right, of elements of a different type. Arbitrary, I'm not sure if that's correct, because a tuple can have like 2 or 3 or 4, 5, 6. Well, tuple has 2, right? That's why it's named tuple. But it's not like a list. We can have infinite lists, and we cannot have infinite tuples. That makes sense kind of in a functional way. Like an infinite data structure is a structure that can only have the same type. For me, like logically, it makes no sense that an infinite data structure such as a list can have a heterogeneous data type, because that would be completely arbitrary. I mean, I don't know what would make it a list then. I guess it's an interesting, idea. That means that we can have a list of integers and a list of characters, okay? And now a list. We have a list, a lost numbers, okay? Lost numbers, and we're gonna put it, yes. We're gonna put it inside of a variable so we can call it. And let's just use the same what he used. 4, 8, 15. You don't have to put space after comma. I don't know why am I doing that, but 42. And I should put space even after this. Yeah, okay, anyway. Lost number, right? So if I write lost number, it outputs the list without the spaces, of course. That's interesting. Okay, so that's the lost number. Yeah, lost numbers. All right. As you can see, why are these lost numbers? Yeah, I don't know. As you can see, lists are denoted by square brackets, and the values in the lists are separated by commas. If we tried a list like 1, 2, A, 3, B, C, 4, we try that, Haskell will complain that characters, which are by the way denoted as a character between single quotes, are not numbers. Speaking of characters, strings are just lists of characters. That's what we said before, yeah. Hello is just syntactic, so a string, hello, is just syntactic sugar for HELLO, because strings are lists. We can use list functions on them, which is really handy. I guess someone, if it's not familiar with it, this is not clear. Maybe syntactic sugar. Sugar in the sense that, yeah, I won't get into this, but I think like what is syntactic sugar in few words? Yeah, just give me this in few words. Sugar is a feature in programming language that makes code easier to read and write without adding new functionality. Yeah, but in Haskell terms. In Haskell refers to concise, more readable syntax constructs that simplify complex expressions or patterns transformed into more fundamental language features by the compiler, enhancing code clarity and ease of use without changing the underlying functionality. Okay, examples include list comprehensions, do notation for monads, and function application with infix operators. Okay, well, I guess we'll keep a note of that. This is done by using the plus, wait, no. Okay, so this is, I guess this is how this string is represented, or how the compiler sees it. Because strings are lists, we can use list functions on them, which is really handy. So this is the reason why the list functions work. All right, a common task is putting two lists together. This is done by using the plus plus operator. Now, one thing I noticed in the, do I have the book here, Effective? Yeah, I bought this book too, if someone is. I found, yeah, this here. We can join strings in Haskell using this kind of a diamond. I don't know how you call this. Using this thing, right? Operator like this, and some code bases, especially older ones, you might also see the plus plus operator being used to join strings. Like plus plus this. The plus plus operator is a less general way to join strings, to join things. The plus plus operator is a less general way to join things, which means it only works with some things, right? And it only works for lists and plain Haskell strings. What are Haskell strings? Or just plain strings? Not clear. Since the diamond sign, I'll just call it the diamond, I'm not sure if that is the correct term, is more general and more commonly used, we'll stick to it throughout this book. Yeah, okay. Not 100% clear. Let's try both. 1, 2, 3, 4, and 9, 10, 11, 12. Okay. 1, 2, 3, 4, plus, plus, and 9, 10, 11, 12. 1, 2, 3, 4, 9, 10, 11, 12. Okay. Let's do 1, 2, 3, 4, and the diamond sign, and 8, 9, 10, 11. Yeah, it's the same. What's the type of it? Yeah, let's do this. What's the type of it? No, we can't check the type. We check the type of this. How do you does ChatGPT know that? In Haskell, what is the difference between plus plus and this one? Oh, this is nice. The ChatGPT now puts what I ask on the right side, like with messages. Okay, the plus plus operator, a type. How can I see the type of the operator? Wait, can I do it like this? Type. Oh yes, maybe it will work like this. No, it won't. Type AAA. Used to concatenate lists. Okay. Yeah, the plus plus operator is specific to lists and is not defined for other types of values. This is a semigroup oh. Semigroup. It's also AAA, but this is semigroups. Used to combine values of any type that is an instance of the semigroup type class. Hello world for string, which is an alias for character. Sum 3 and sum 4 result sum get sum 7. Oh, you can do stuff like this. Product 3, product 4. Can you like, what would do if I like do this? No, I can't do it. All right, let's move on. A common task is putting two lists together. We did this. And then hello. This is just doing hello plus space plus world. Hello plus space plus world. Hello world. These are all really basic stuff. Wood. This is just same thing but with characters. The one they here in plus plus ut. Okay. Watch out when repeatedly using the plus plus operator on long strings. When you put together two lists, even if you append a singleton list to a list, for instance 1, 2, 3 plus plus 4, internally Haskell has to walk through the whole lists on the left side of plus plus. That's not a problem when dealing with lists that aren't too big. But putting something at the end of a list that's 50 million entries long is going to take a while. However, putting something at the beginning of a list using the cons, yeah, I know that. Yeah, it's also called the cons operator, is instantaneous. A small cat, 5, 1, 2, 3, 4, 5. Yes, this has to do with lists. That was, I remember the time when I was trying to learn Common Lisp. We have all these, like, I don't have Lisp installed here, but like cons 1 and 2, I guess you would get a list cons. But in Haskell, the cons is represented by, so yeah, like this. Would you get, no, it will maybe like this. No, it's not like that even. 5. So 5 has to be outside. So you have to have a list already. All right. Like this. Oh no, it's already a list. Yeah, but how do you build a list? Yeah, you see. A small cat. This is a string. You add small cat. How do you add numbers? I don't know. Notice how cons takes a number and a list of numbers, or a character and a list of characters, whereas plus plus takes two lists. Oh yeah, the cons. Oh, that's why. So the cons takes just one. The conses an element to a list. But the plus plus or the diamond sign, right? It can concatenate two lists. Even if you're adding an element to the end of a list with plus plus, you have to surround it with square brackets, so it becomes a list. 1, 2, 3 is usually, it's actually just syntactic sugar for 1, 2, 3. 1 cons 2 cons 3 cons an empty list. Oh, I wasn't thinking functionally. You see, this is a really simple example. But the thing is that I was doing like the beginning of the list, right? Cons to 1, cons to 2, cons to 3. Let's say stop at 3. Cons to the end of a list, which is completely wrong. I should cons to 1, cons to 2, cons the 3, and cons the empty list itself, right? And then I will get a list. So even the list itself it's like abstracted. So it's not like the beginning of the list, 1, 2, 3. That's actually a very imperative way of thinking, like the beginning of a list plus 1 plus 2 plus 3 plus the end of a list. You do 1 plus 2 plus 3 plus the empty list. This is more functional. Yeah, this is just, it kind of makes sense when I look at it now. But before it didn't, you see. 1, 2, 3 is actually just syntactic sugar for 1 cons, 2 cons, 3 cons, empty list. Empty is an empty list. If we prepend 3 to it, it becomes a list of 3. If we prepend 2 to that, it becomes 2, 3, and so on. So you could basically just have a list of a number. So 1 cons, an empty list, you get a list of one number. So could you cons a list to a list? Yes, you get a list of lists. But how do you cons an empty list? Like, Can I do just cons an empty list? No, I cannot, right? Can I take out a list of a list? Yeah. Note, empty list, the list of an empty list, the list of a list, and the list of an empty list, the list of a list of an empty list, and then the list of a list of three elements, which are an empty list. Three empty lists are all different things. The first one is an empty list. The second one is a list that contains one empty list, all right? And the third one is a list that contains three empty lists. Well, that's nicely said, much better than me. See, even after 8 years, I still can't. If you want to get an element out of a list by index, use this exclamation 2 times. The indices start at 1, at 0. So this is a very, even the first time when I saw this, I didn't like this. It's because it didn't seem, functional. So if I have a string and I do this and I do like a 0, I get an, get an A. If I do 1, because we count from 0, right? Computer programmers count from 0, and I won't explain that, but there are like even some jokes. So if you Google that, you'll find it. Anyway, Apple indices, so twice exclamation mark and a 0 gives A, 1 gives P. Yeah, but it's like you have to, I don't like it because it's like you have to inspect what's in Apple, right? Like how do you do this without knowing what's inside of here? I guess if you have some kind of a data structure that, yeah, this is, and I don't know what's the cost of this. This doesn't look, yeah, well, anyway, that's how you can do this. How are we with time? 30 minutes, all right. Steve Buscemi, yeah, 9:31. Okay, but if you try to get to the sixth element from a list that only has 4 elements, you'll get an error. So be careful. You see all of these warnings, that's not really functional. So be careful. Like I want to have an abstraction that can encapsulate that. I don't want to like be careful. So if I do Apple, right? And I do this, and let's say 7, because Apple has like what, five letters? Oh, index too large, call stack, error, call that libraries, blah blah, base lists, base GHC list too large, call that libraries, base lists, call that interactive, yeah. So it's too large, index too large. Okay. Lists can also contain lists. They can also contain lists that contain lists that contain lists. Okay. B. Okay, now he's like, I'm just gonna copy this because I mean, it's nice to type things out as I do with Nix, but this is like, okay, fine. We have a B. So this is a list that contains 1, 2, 3, 4 lists. And B plus, if we add B plus 1, 1, 1, so we add B plus a list of a list 1, 1, 1. So now what do we have? You see, so we had, if we added a list, what would we get? So if we do like, will he do it here? Why is this the same? Yeah, I was just confusing because if you add a list that contains a list, you kind of expect, okay, it makes sense because we have a list that contains lists. It's like this 1, 1, 1 gets inside. Let's add 2, B plus, let's add 2 like this, 2, 2, 2. Oh, why is this not working? if we do the same thing as B plus, let's like do. Yeah, now it works. Where's the 111 list? Yeah, I don't know. I can't explain this actually because we did add it one. Does it destruct? No, but why didn't add? Let's add 3. No, it changes. And I still can't add the... No, let's do 4. No, I cannot. So yeah, this is he const, but he can. Why can I can cons? Oh, it doesn't. Yeah, you see the list is the same. This kind of like it's gone even after we add these two lists. Oh, that's why. Yes, we have an immutable lists. Lists are immutable. So even if we add something to our list, yeah, it kind of tells us, all right, your list is going to look like this, and then you like. So if I call the B list again, look, you see it's not the same list. If we add 1111 to the list, we get that list will be added. But if I check the B again, it's still the same thing. So I would have to redefine B. You see, I would just really have to like, where did I define? Like I would have to like redefine B to keep it like 1, and now the B would be, you see, now the B would be different. All right. Functional programming, welcome. B index 2, yes. Now it gives the entire sublist, so to say, because indexes work on elements of a list, and this list has how many? Well, you don't count the numbers, but this is the first, this is the second. Can you hear the bells? Maybe not. The lists within a list can be of different lengths, but they cannot be of different types. Okay? Just like you can have a list that has some characters and some numbers, you can have a list that has some lists of characters and some lists of numbers. Oh, that's what he said with few characters and few numbers. Lists can be compared if the stuff they contain can be compared. Lists can be compared if the stuff they contain be compared. I like this kind of Haskell-like definitions where you kind of define the thing which you, and then you almost end up saying, well, of course, but it's kind of, it's nice to put it into words. Like the lists of things can be compared if the stuff they contain can be compared. Yeah, it makes sense. When using less or equal, greater, and greater or equal to compare lists, they are contained in lexicographical order. Oh, lexicographical. I'm not sure what's the proper term, alphabetical or lexicographical, because I heard both. Maybe alphabetical because it starts with an A and lexicographical starts with L. That's a bad joke. First, the heads are compared. If they are equal, then the second elements are compared, etc. So it's like works some kind of a layout rule. 3, 2, 1, it's not a layout rule. 3, 2, 1 greater than 2, 1, 0. So 3 is greater than 2, 2 is greater than 1, 1 is greater than 0. That's true. So 3, 2, 1 greater than 2, 10, 100. True. So it compares 3 and 2, but then 2 and is let, so it kind of the first one, the head wins. So if the head is greater, so like if I have a list and I have 2 and 1, 1, 1, 1, 1, 1, 1, 1, 1, is that is that greater than is that greater than 1 and then 5566666? True. Yes. But what if I put here 3? False. So it only, oh yes, that's the lazy thinking. And because lists are infinite immutable data structures. So if 2 is greater than is false, so it's not greater than 3, then it makes no sense to compare the rest, even if the rest is all in the second list is greater than in the first, because the head of the list is, the head of the first list is male, sorry. Yeah. So this also has to do with functional thinking. So you look at the first, you look at the head, you compare the head, and you write false. Yeah, there's a better, more eloquent explanation of what I'm trying to say, but it's good to think about this thing. What else can you do with lists? Here are some basic functions that operate on lists. Head takes a list and returns its head. Tail, this is like we're talking about dragons, you know. Head takes a list and returns its head. The head of a list is basically its first element. So we have a head of a list. What do we have? 5. Let's say 1, 2, 3, 4. We get 1. Would it work with like apple? Yes. So when we do a head of an apple, we get an A. And the tail would be then pull. So you could do stuff like, maybe I guess you could do like, let's put an apple in a, let's say my string is apple. It's a longer string than the apple. That's a bad name. Yeah, okay, let's make it more, confusing. A is apple. So now head of A plus tail of A. Couldn't match type, actual string. So if we do head of A is A and tail of A is pull. We would have to cons it. You see, head of A cons with tail of A. We get an apple. All right, you see these little things? Tail takes a list and returns its tail. In other words, it chops off a list's head. Okay, wow. Chopping things. Last takes a list and returns its last element, and init takes a list and returns everything except its last element. So basically last is like the reverse head and init is like the reverse tail. Depends from which side you're looking at, right? If I have a list of like tail, right? Tail 1, 2, 3, 4, I get 2, 3, 4. But if I want to get the tail from the other side, right? So I'm getting the tail from this side. It's 2, 3, 4. The head is 1. And the tail from the other side is init. So init 1, 1, 2, 3, 4, and I get 1, 2, 3. So that means, the last is the head. The last is the reverse head. So the last is the head of the tail. That's the head of the tail. So I guess you could say the head. Well, we can now mix them, like head of the tail. Well, no, this would change the direction. the head of a tail. No, actually, let's do this. The last, okay, let's put this in a string. No, not a string, in a variable. A is, let's call it list. 1, 2, 3, 4. So now check this out. So the last of a list, maybe this is confusing, last list. The last of a list is the same as the last of the init, no, the last of a tail of a list, right? It should be the same, true, right? Because the last of a list, which is 4, so that's the reverse head of a list, is the same as the last of the tail of the list. So the tail is 2, 3, 4, which it's still the last thing is going to be 4. So you can kind of prove things like this. You're basically proving things. Or you can reverse it, like the head of the, yeah, I won't do it now, but you can play with this stuff. Like the head of the init is the same as the last of the tail, and the tail of the last plus the head of the init is the same as, this is not true what I just said, but I was like you can think things, you can go through these things, and that's really fun. If it's fun, why am I not doing it now? I'm too tired. Yeah, actually, Eric Mayer had this proof. Let me. Oh, wow, I just found a huge rabbit hole, like the Stack Overflow. How ways to get the middle of a list. I'm slowly getting through Eric Mayer's lecture on Channel 9. 14 years ago. Wow. So the ways, so many ways you can get the middle of a list. And one user said, like, the list is an infinite data structure, so you really can't. So it's not efficient to get a middle of a list, because yeah, if it's infinite, how do you get the middle? These are all interesting. This is so deep. So yeah, the right data structure for the right problem. In this case, you've specified something that only makes sense on a finite list. There is no middle to an infinite list. There is data sequence, which are finite lists in Haskell. Data sequence. So yeah, I guess it's not called a list. It's, oh, it's a broken, it's a broken link. So data sequence, that's a finite list. Finite list. The sec a type represents a finite sequence of values. So it's even not called a list. Sequences generally behave very much like lists. Filter, lookup. Yeah, it's nice how it has a logarithmic time. Data sec empty. Yeah, okay, let's go back. These are really rabbit holes. And in programming, Haskell from Grant Hutton, they have some kind of small how do you call it, small assignments, like, weird to use that word in a functional programming language, assignments, where you can use these kind of to find a new way to extract things from a list. Tail last takes a list and returns its last element. I think to, like, I could spend now time in this, but I won't. Not because I'm tired, but it's just, I think, I want to go more. I want to do more. This is something what I always did, and it kind of, you do it a little bit, then you get bored. Maybe you need to progress a little bit more and then come back to it. Yeah, I'm not sure. Well, I do understand now. So we have the head and the tail, and and the last and the init, which are like the reverse from head and the tail. The problem with all of this is like if the problem with these is that if I do like a head of an empty list, you know, I get an exception, which is really bad. Empty list, call stack, error. So if you don't have anything in the list, or if somehow my list, that's why these functions are not great. Like, okay, but these are the basic, I think these are like the basic atoms of our abstractions. It's important to understand how they work, I guess. Let's move on. If we think of a list as a monster, here's what's what. Init, last, head, tail. Yeah, I don't know how does that help if it's a monster. But what happens if we try to get the head of an empty list? Exception. Oh my. It all blows up in our face. If there's no monster, it doesn't have a head. Okay. When using head, tail, last, and init, be careful not to use them on empty lists. Yeah, I guess it could be said, it would be clear if you say like last and init is like the head and the tail turned from the other way around. I think then it makes sense. I remember the first time when I read this, I was like, okay. Be careful not to use them on empty lists. Again, this be careful, which I don't like, because we have to be careful about something. You're not supposed to be careful. You are supposed to be careful, but the Haskell, well, we should use abstractions, right? This error cannot be caught at compile time, so it's always good practice to take precautions against accidentally telling Haskell to give you some elements from an empty list. Yeah. Well, it's like telling a child, you know, watch out, and they're still going to do it. So we need better abstractions. Length takes a list and returns its length, obviously. Okay. So length of a 5, 4, 3, 2, 1 is 5, as in 1, 2, 3, 4, 5. So length of a apple is 5, also 1, 2, 3, 4, 5. So it's interesting that length does not have an exceptions, right? It can always, even if it's an infinite list, it can return it, right? Length of a, will this work? No, I will not try this. Length of a 1, 2, 1, and this. I think this will not work. Should I do it? No, I'm afraid to do it. I won't do it now. I'll do it when we do infinite lists. Because I think the length of an infinite list is an infinite number. So I think it will just stop, or it will just halt, you know. So a length, all right. So you could do like a length of an apple plus a length of an apple. That should be 10. Yeah, because a length is a number. And even a length of an empty list should be a 0. So yeah, you can use this. Now null checks if a list is empty. Okay, so then you could check your head. Check your head with null. If your head is empty, no. Null checks if a list is empty. If it is, it returns true. Wait, I have to check something. Right. I've changed the light and now it looks like I'm on fire. All right. Null, check if a list is empty. If it is, it returns true. Otherwise, it returns false. You can make kind of your exceptions could be made safe with null. So it's like, let's do if head of an empty list is empty. If head of an empty list, no, how would you check this? If list is null, then empty. Oh, else not empty. Wait, if let's say 1 2 3 4 null, then empty, else filled. No, it doesn't work like that. I'm doing something wrong. If list null, I'm not sure how to check null. Null of an empty list. If null, maybe if null list, if null 1 2 3 4, then true. Empty. Else not empty. Not empty, right? And if null of an empty list, then empty, else not empty. Empty. All right, if null, then empty, else not empty. So if head of an empty list is equal to null, maybe it will cool like if head of an empty list is the same as null of an empty list, but that's not the same. Yeah, not sure. Null checks if a list is empty. If it is, it returns true. Otherwise, it returns false. Use this function instead of x's if you have a list called x's. Can you hear the seagulls? Null 1 2 3 false. Null empty list true. All right. I gotta admit, this is not the most exciting part because I think almost most people can understand this. And they kind of, they make sense. Like reverse of a list reverses a list. So 5 4 3 2 1. So you could do like reverse apple helpa. So you could make some kind of what do you call this? Palindromes. Maybe there is a function. It would be fun to like code a function like that. Takes a number and a list. It extracts that many elements from the beginning of the list. Watch. Take 3, take 5, right? Let's do take 5, like the song. 2 3 4 5. Take 5, and it took all 5, right? Take 5. 1 2 3 4 5. So that's like the tail. No, that's not like the tail. If I take 4, 1 2 3 4 5. 5. Yes, that's like the init. Let's compare. Take 4 of 1 2 3 4 5 is the same as init 1 2 3 4 5. Why is this false? Init. Oh yeah, because I only added, if I had 3 here, it will be like, yeah, true, right? So take 3 from 1 2 3 4. We get these 3. 1 2 3, right? Take 3. And init from 1 2 3 4 takes, it's like the reversed tail from this list. So we remove the end, the last of the list, or the head if we turn it around. And the tail of it, the tail of the end of the list is same as take 3, right? Okay. Take 1, take 5. What is it? Take 5. Oh, there's something weird going on. Take 5 of a 1 and 2. 1 and 2. Take 5 of a 1 and 2 and 3. 1 and 2 and 3. This is not good. We don't like this. Because you could say take 5 from 1 and 2 and 3. See, this is again, you have to inspect what's inside. I have 1, 2, 3, and I ask it take 5, and it gives me 1, 2, 3. So it ignores the part that does not even exist. Take 0, takes an empty. Okay, see how if we try to take more elements that there is in the list, it just returns the list. If we try to take 0 elements, we get an empty list. Yeah, but why is that? Why? Yeah, I don't know why. Drop works in a similar way, only it drops the number of elements from the beginning of a list. Drop 3, 1, 5, 6. From the beginning, drop 0, 1, 2, 3, 4. Drop 100. From the beginning. How is drop 3? I don't get this. Drop 3 from 1, 2, 3, 1, 2, 3, 4, 5. Drop 3. Oh, it drops them. Yeah, this is confusing because when you do take 3, it takes the first 3, right? When you say drop 3, you kind of expect, okay, I will drop this 3. It's the same as take, but drop is like it erases them, and it gives you the list. It gives you the list without the 1, 2, 3, without the first 3. So like drop 3 is like without the 3, and which are at the beginning of the list. So I guess you could also mix this, like drop 3 of the reverse of the list. Yeah, right. Like drop 3 of the reverse of the 1, 2, 3, 4, 5. And then you get 1, right? Because you reverse, so you get 5, 4, 3, 2, 1. And drop 5, and you get the 1. You see, you get the 1 now because it's the reverse. You see, you can do all these kinds of things with take, drop, init, last, head. I don't like that so much because there are a lot of words, and these words have meanings, and they don't look like some mathematical structures. I mean, it is functional, but it's like drop and take. Almost like sounds very imperative. Maximum takes a list of stuff that can be put in some kind of order and returns the biggest element. I guess that works with, we did the max and the min. Minimum returns the smallest. The max, we don't have the max, right? The type of a max. We have the max. Yeah, but max works only on tuples, like, yeah, like max 1 and 2. Oh, 1 and 2. And no, it won't work like that. Max 1 and 2, it gives you 2. Yeah, max 1, 2, 3, it won't work. Yeah, max 1 and 2, it gives you 2. It works only on 2 numbers. Does it work on A and B? It does. It only works on 2 elements. Compares them. But this works on lists. Maximum, the gladiator. So maximum gladiator, we get a T. The maximum of the gladiator is the T. So the maximum of a 1, 2, 3, 4, 5, 6, 7 is this 7. Same thing with minimum. The sum takes a list of numbers and returns their sum. Let's check the type of maximum. Foldable. This we still don't know that, right? Foldable. It's like it folds them, I guess, and then it takes the highest one. Order A, TAA. Yeah, this is still not clear. Sum. We have a sum defined. Foldable T, num A, TAA. Was the same like the maximum, but it works on numbers. Yeah, so that's this example. Like if you have a sum 1, 2, 3, 4, 5, so it sums the list. This is amazing example, right? Just sum this. It's almost like the length, but it's not the length, right? It's length 1, 2, 3, 4, 5. So the length of the list is 5. And Yeah, I almost wanna like compare sum and the length of these lists. What's the connection? I won't do it now. The product, okay. Product is same as sum, but I think guess this is the way to get the factorials. Product 1, 2, 3, 4, 5. That's 24. Okay, it's the same as the sum. It's just, works with multiplication. Elem takes a thing and a list of things and tells us if that thing is an element of the list. It's like the indexing, but it checks if it's there. It's usually called an infix function because it's easier to read that way. So it's like is an a lm of the string apple, and it's true. Is like, let's say, a b, which is not in the string apple, should be false. Yeah. Those were a few basic functions that operate on lists. We'll take a look at more list functions later. Well, this was kind of boring, but it shouldn't be boring. Not boring. It shouldn't be boring. No, I think you know why am I like this? I think maybe this, I don't know, maybe this happens with the rest, but sometimes like you start to learn this language and you start playing with lists and it goes really fast, and but I guess this is not hard because you're kind of still working with values and manipulating with values, like using basic operations on a single abstraction layer. Like these are not like, it's not like these. Yes, we did. You can mix them, like the length of and then the head of the tail, right? But these are not basically levels of abstraction, as in a function that has a sort of like a meta rule, a rule that has a rule. This is what for me was at first very confusing. Like there is this a rule, like with a monad or like something. There is a rule, and that rule itself has rules, which is a very cool idea that can even help in life because we sometimes think really hard about rules. And just the idea, just contemplating that some rules have rules, kind of okay, like a bit opens the mind a bit. Yeah. I mean, personally, I just find that helpful. Drop works in a similar way, only drops. Okay, we did this. Yeah. Texas Rangers. All right. How long was this? Hour and 7 minutes. This is really long. Maybe I look like I'm on fire. Maybe I should stop now because I don't want to make this too long. And this is going to be an interesting one. Texas Rangers. Cycle, repeat, replicate, and list comprehensions. All right, list comprehensions. This is going to be nice, interesting. And then tuples. Oh, he goes then with the tuples. After lists, we do the tuples and then the functions on tuples. Zip the tuples. There's an example. Oh, with a triangle. Yeah, triangle. ABC using the list comprehensions. Types and type classes. Okay. All right, then he goes into type classes. Then he introduces, so the Graham Hutton did this actually before doing the operations on lists, which is interesting the way you approach. And then syntax in functions, pattern matching. You see? And Eric Mayer did this with the conditionals, pattern matching. He did this right after it. So, I mean, these are like cognitive leaps, how you progress in learning functional programming, vectorials. He's doing here with vectors. So this guy, yeah, he did a bit more. This is a bit more mathy, these examples. Add vectors, like adding vectors. I remember this in high school. Adding vectors, yes. First and second. These are again lists. Guards. Pattern matching and guards. Yes, so these are guards. Where? Yeah, sometimes where is introduced really at the beginning with let statements. Yes, with let statements like Haskell programming from first principle introduces where with let statements. Let it be. Oh, he just introduced it. Ah, he introduced let now. Let bindings. Interesting. Case expressions. So this is all still kind of recursion. Yeah, I can't stop now. Recursion is going to be interesting. Maximum, maximum. This is going to be interesting. All right, but still the basic abstraction layer. Although getting into the concept of going deeper and deeper and deeper. Yeah. Yeah, like this. Yeah. Zip quick sort. Oh, this is the quick sort. So the quick sort is the example that Graham Hutton used in the beginning as like a small taste, as he called it, small taste of Haskell. And then he came back to it, and also in Graham Hutton. This is nice, this picture. Think recursively, higher order functions. And now we are, oh, now he does the curried functions, Haskell curry. So he introduces higher order functions with currying. High order. So what are high order? Apply twice. FFX. Oh, he introduces it. Yes. So it's like you apply a function on a function on a function, because yeah, so far we have been only working with values. Okay, functions are values, you could say, but we're working like with basic values, like with numbers and characters. We're not really working like this. F of x is apply twice, right? Apply twice fx. So you see, it's not just like we did something and we only input one thing. Here we input two things, and one of the things is a function, and we have a type here. So apply type, apply twice, apply twice is not just something that takes an argument of some type and outputs the result, but is something that takes a function of this type that takes an argument. So it takes a function that takes an argument of this type and outputs an argument of that type. And that itself, right? Yeah, I can, you see, but this is a bit more complex. So apply twice. Fx is f(fx). Okay, this is almost simple. So f of x, and then another f is applied to the result. Well, that's like the double. Apply the double twice. Apply twice double x. So yeah, wait, let me try. So double is lambda x. So let's just use a simple one example. I like lambdas. Double x is x plus x, right? So apply twice. Double x is double x, right? That's it. If f is double, f is just a function. So apply twice. Double x is double x. This should work. Apply twice. Oh, what do I do now? Apply twice. Oh, this is not a good function because I have to write again. Like, look, I have to write the double because this is more general. Yes, because this is more general because I can do a double here or anything I want. Apply twice. This is just more. This is smaller, or I don't know what's the word. Can take any function, I guess. But okay, apply twice, double 2 is what? This should give us 4 and then 8. Yes, it works. It gives us 8. Okay. So okay, he goes slow. It's not bad. Zip with I've never reached this part. I tried to read this book. I think I did reach this part. Maybe I did. Maps and filters. Okay, these are cool things. Maps and filters. So this should not be a problem. Lambdas. We love lambdas. It's interesting what he will do with lambdas. I don't remember because like Haskell programming from first principle, the first chapter is about lambda calculus. And I kind of, you read it and you kind of get it, but then it's too short. Folds and horses. Fold is cool. All right, folding. Scan. Function application. All right, with a $sign. Function composition. Wonderful. We love composition. Modules. And then he goes into modules. Interesting. Suppose, concatenate, or again, kind of. Yeah, these are kind of stuff what we did today, but I guess with sequences or what? Element from a list. Wow. Oh, that's how he builds up. Look at this. It will be like we did take, right? And take was just like take three. Take three from a list. Simple. We do this in life. Just give me two things from, give me two pairs. I go and buy two. There's a list of pairs in the shop and give me two pairs, right? And somebody gives us two pairs. But it would be really weird if you go and buy fruit and you say, you know what, give me take while. It takes elements from a list while the predicate holds. And then when an element is encountered that doesn't satisfy the predicate, it's cut off. It turns out this is very useful. Well, we do that too. Like, give me those two pairs, but only if they look great. Or give me those two strawberries, but I don't want them too soft. Yeah, we do that too, right? Like I want them sweet. Are they sweet? Can I try? then you try. That's at least where I live from. I go to the market and sometimes you can like, can I try? And they said, sure, try. So you try and it's good. So this like take while, not like take. So we do all these things. Sorting, yeah, we do all these things. Find index. Yeah, I guess these are not the most exciting things, but it's important to get the basics. I think it's important. Ooh. Data character. I'm still continuing. I want to see data map. Find key. Maybe, though, this is maybe here. Interesting. This is a long one. Null singleton lookup. From list. Bigger lists. Map from list max. Yeah, these are more. I guess this wouldn't be, someone could get like overwhelmed with such examples. I guess he did a lot of math. So import from list. Making our own modules. Oh, this is interesting. Yeah. Import. He's going to make a module, and then the program has several modules with defined functions. That's like in NixOS when we have the configuration.nix and we import the home nix or something, whatever nix, that has defined functionality. Stephen Deal did a great blog post. I think I don't remember it, but Stephen Deal, he writes great stuff. He really knows Haskell, right? Making our own types and type classes. Algebraic data types intro. All right. We like algebraic data types because they sound great. Algebraic ADT. Record syntax. Yeah, record syntax, like a type of programming, begins already with a record data type, which is kind of cool. He does this transformation between seasons. Maybe nothing and just a. Yeah, this is the problem what we had with the head of a list, because if we give an empty list to the head, it gives us an exception, and if we have like something like a maybe, then we can encapsulate that thing when we do not receive something, when we receive something that we don't expect. So we expect something like this or just that, but if we get nothing, that's encapsulated within here, and we don't get like an exception. We got an empty list. What do we do with it? This is like, oh, we got nothing. That's fine. We know what to do with it. Just label it nothing. Data order. I'm kind of looking when are the monads coming. I just want to prepare it's good to prepare yourself. Like I think it's good to just run through it maybe and see like what's going to happen. Recursive data structures. Oh, he introduces the list here. Like, how is the list actually defined? And understanding recursion becomes important here. Oh, this is going to be so long that I'm going to be doing this series. Maybe, probably in a couple of years. Type classes. Where are the monads? Give me monads. A yes, no type class. Monads. Where is the monad? Kinds. Oh, kinds. This is the Zen master kind. Kind Zen master. Input and output. That's a monad. Is that a monad? Okay, we'll stop now. I don't want to. I'm going too far. Yeah, I'm going too far. So interesting, right?